Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everybody to this session of the Microsoft eScience workshop. And this is our session which I gave the name to, which is Advances in Software Support. Many of the other sessions in the workshop concern how we use computing in eScience, and this one is perhaps the one which is particularly different and comes from the bottom. And how do we support all of these wonderful application packages which the other sessions are all hearing about. So we've got two papers here today, and the first one is going to be given by Sujia Chu, who's from the University of Maryland, not too far from here, down south. And he is a research professor there, and his paper is entitled Software Support for Hybrid Computing. Over to you. Yep. So, here we go.
Thank you. Do I have pointer? Do I have pointer? Laser pointer. Laser pointer? That's fine. Okay. Top one? Yeah. Okay, thanks. Good morning. Today I will talk about the software support in hybrid computing. And the name I want to clarify here is hybrid computing here means how we connect a conventional computer, consists of like IBM's PowerPC or maybe Intel or AMD with accelerator like IBM Cell and GPU. And we will talk about what kind of software can be used for this kind of application. I will first talk about the background behind this, then I will talk about the hybrid computing architecture. In particular, I will talk about the GPU and IBM Cell, because that two is the popular one used in the accelerator. Then I will talk about three software apparently can be used for this hybrid computing architecture. And the first one is from IBM. The second one is really widely used in high-performance computing community. And third one is coming from the business section, but we apply to high-performance computing. And I give you a summary. I want to mention the software I'm talking about here. I'm not really talking about real low-level programming like a socket. And all these three packages actually based on socket. The background here really is we see the trend is the microprocessor really from the single very powerful processor to multi-core. And you can see CPU have like 2, 6, even 8 right now in the Intel, like something like a Nihilium. And a few years ago, IBM Cell come out, actually associated with the Sony PlayStation number 3, but they have 8 SPU. Later on, you have NVIDIA have make their traditional GPU convert into the general purpose GPU. Now you have like a 1,100 more streaming processor. So really you have a lot of processor, but it's tiny processor, but that can be used for general purpose data parallel. So it's really, for this conference, we talk about data intensive, and the GPU, also IBM Cell, actually can be good for this area, okay? The question really is, how can we utilize this powerful computing to do some application? So I want to use this diagram to show the current computer system consists of the accelerator. This is the way the people doing the so-called data intensive or compute intensive calculation is like cluster. Consists a lot of, say, Intel blade. But now you have some new accelerator come out, like an NVIDIA GPU, and this the GPU, and you can plug in as one of the graphic card. And now you also have the IBM cell blade. This is actually from the same processor used in the PlayStation 3. But if you want to connect the GPU to the cluster, you have to have something like the CPU to connect the GPU into the cluster. And for example, like in Intel Nihilium, this is the latest cell Intel blade. For the IBM, you can really connect to the cluster. But the fundamental question here is, you have this kind of hardware, and it's like a commodity hardware. How can you connect to the cluster? Okay. In addition, you want to utilize this hybrid system to do some application. For example, like climate. I think right now climate research is getting a little bit interesting because of global change or global warming. For example, if you do the global warming investigation, you have to understand how the energy come in from sun, and how they be absorbed by the cloud and reflect back from the earth. And you have to understand this kind of physical modeling. And this kind of modeling is perfect, good for utilize the GPU to accelerate. And this is the whole thing we want to do for the hybrid computing. Just give you a very quick brief view on the climate model, because that's the thing we target. So if you do climate model, or even weather part, depending how much physical thing you want to model, you really involve a lot of components. But some part is very not compute intensive or data intensive, but some part it is very compute intensive. The one we pick out today here is, for demonstration, is the solar radiation, because this is the ultimate the energy source for all the climate change. So this is really NASA production code to do the climate, or maybe you can say near-term weather forecasting. You can see there's a lot of components inside the model. The model can be like, say, 100,000 line of code. But if you do the profiling, you found out that only a few components can be data intensive or maybe compute intensive. The one we talk about here is the one solar radiation, and this very, very compute intensive. And if you really break down the profiling of the performance, the dynamics part, which really calculate how the air circulates around the Earth, can be probably, say, 25%. But radiation part in total can be another 20 or 25%. So if you really can speed up the solar radiation, you can really contribute the whole calculation, reduce whole computing time. So if you do the climate modeling, basically the way it's the same thing for do the data decomposition. For the thing we deal with, so-called physical modeling, basically is how do you model data in one column, okay? So 2 years ago, we started a project try to see how can we utilize IBM cell. The reason to use IBM cell here is, at that time, if you want to use Intel core, say the peak performance, say 10 gig, okay? But at that time, IBM cell can be like 200. So immediately you had a 10x performance improvement. That's really the reason behind people want to use accelerate, because you can get like a factor 10 also performance improvement. Okay, so we did this kind of investigation. What we did here really is we decomposed the model into the grid. Then we also decompose data along vertical direction. So if you want to utilize the IBM cell, for example, you have to really figure out how to map your data into the smaller memory inside each smaller core. And this only has 256K. But for regular Intel, people normally use 1 gig. So that's really the problem. If you want to use any accelerator like GPU or cell, you have to really pay attention. How can you do your data decomposition from traditional like Intel, like 1 gig or 2 gig memory, into the accelerator, which only maybe have, say, few K. In this case, maybe 200K. That's really the challenge. We did the porting and spent some time to do cell coding. We actually get very good performance. And you can see the green bar is the one we use cell. Okay, And this yellow one, for example, is from, at that time, the latest Intel core. Okay? If you look at the Intel process performance, individual core is not really improve the performance a lot. It's still like, say, 10 gig flop, maybe 20 gig flop, but they add a lot of core. Okay? So here we can get like a probably 10x improvement. Use one IBM cell processor against one Intel core. Okay? I think that's really make people happy, because if you can do some kind of physical modeling, if you can accelerate certain part of the component, basically scientists can add more complexity into the modeling. So you can really even get more science out of this. Okay? Then we do this, we think, oh, this is really nice, but how can we connect to, the major computing platform? Because if you run the big calculation, right? If you talk about, say, teraflop data or maybe petaflop data, you cannot use your single machine on your desk. You have to involve something like cluster. Okay? But now the question is, how can you connect the accelerator like IBM cell to the cluster? And this is really the fundamental problem very few people have touched. I know a lot of people do the investigation on GPU or cell, but that's only doing the investigation on desktop. How can you connect the accelerator to the main cluster? I think that's still the open question. So now the GPU getting more popular because everybody has GPU. Even my Mac has GPU. But if you look at the GPU programming, they pay more attention to desk computing. Really, how do you connect the GPU to your CPU? But they did not say anything about how you connect your GPU to the cluster, because that's not their major market. So if you look at the GPU programming, you can do the GPU coding with say NVIDIA CUDA. But now you have industrial standard. That's probably give you some certain hope. You can do something in standard way, and you have OpenCL come out. But if you want to connect the GPU to CPU, you have to use CUDA or maybe OpenCL. But the question still remains, how can we connect the GPU back to the cluster? But in current way, you have to still using hosting CPU. Okay? For GPU computing, just like a cell computing, basically you still need divided data also computing between the CPU and the GPU. You want to make sure the data intensity or compute intensity on the GPU and the management on CPU. If you want to connect your GPU into the cluster, you have to make CPU to connect to other GPU. I just want to try to make comparison. For GPU and the CPU and the cell, it's very similar. So that's why I think what we talk about here really can't apply to GPU, also the cell. But I emphasize the cell today. Basically, the CPU in case of cell is really corresponding to the main CPU in a cell. It's like a PPE. Okay? But for the GPU, you have like tiny individual streaming processor. That's corresponding to the cell individual SPE. So these two things really match each other. The difference here is IBM cell, they pack everything in one chip. If you do GPU and you have to use PCI Express card to connect this thing, this can be much, much slower. And that's the difference. So we look into what kind of software actually can be used to connect your accelerator like GPU or cell into the mainframe computer. So we found out the IBM actually has some package as a part of cell programming package. They try to facilitate coding because cell coding essentially is a little lower level even compared to traditionally people use MPI. So if you try to connect your cell to the cluster, that's even harder. So that's why IBM developed this package, try to ease the programming to connect your cell like accelerator to the mainframe computer. But what we found here is quite surprised. I mean, this package has been released for 1 year or so. But if you look at the web, it's only few people using, but it's really inside of Lausamo's project, like Roadrunner project, because Roadrunner is the one utilize IBM cell and AMD. This is really a hybrid system. And it's the first one break the 1 petaflop performance, but this software somehow is not widely used. So we will not talk about this a lot. So now we look into MPI. MPI is the one that people use in high performance computing. So if you use cluster, if you want to get a scalability portable, most people use MPI. So MPI is really also flexible. That's another way to think about MPI, but it's not easy to program. So the program is quite difficult. The problem related to if you want to connect your accelerator, use MPI. This is really a problem. You have to really split the existing application. There's some kind of application specific communication mechanism. You have to split that communicator so you can really link this accelerator back to the cluster. That's really the problem. If you have code, like say, production code, you have certain complicated way to do the communication, and that can be the problem. Another thing here really is you have to have the MPI installation on both sides, on the accelerator and also on the hosting computer, and that's also the problem. If you want to connect IBM Cell, which is PowerPC architecture, connect to Intel cluster, which is x86, you have to deal with different operating system and also the little Indian and big Indian convergence stuff. I think that's really a problem. But OpenMP doing this, but it's only OpenMP supported. So there's certain limitation how you use MPI to do this kind of application support. But we did this kind of thing, we more or less for demonstration. So what we did here really is we try to do some kind of accelerate certain, say, like particle calculation. That's almost like a data streaming stuff. And you can do that, basically use MPI to set up, this is a cell blade, and this is just PowerPC blade. So MPI is very flexible. You can use MPI to set out this configuration. You have M blade on the cell side and also N blade in the PowerPC side. This is very flexible configuration. But the thing you also need to remember, when you do this hybrid computing, you have to have two different executables, because on this side, you have to use accelerate specific API to do some coding. But this one probably your traditional coding. So you have to have two executable on different architecture. That's the other thing you have to consider. We did a demonstration so we can do the calculation here, then pass over to PowerPC. That's like a management. Then finally, we can go to the hyperworld. We do this successfully. And we can see this is actually real-time calculation. So we can simulate, say, 1 million particle in the cell blade, then go to the PowerPC, then transfer to the hyperworld. So this is real-time streaming. So we can do that, use MPI. Then later on, we found out maybe you can use something a little bit better, because MPI is good, but everybody agree MPI is the low programming paradigm. As I said, you have problem deal with a different architecture, and also you have problem, say, it's only one open source OpenMP to do this kind of thing. So if you were already using Intel MPI, that's supposed faster, you may run into the problem. So we try to do something, maybe do some application which may not use MPI. So then we found out the IBM actually developed another software called Dynamics Application Virtualization. So what they do basically is, originally designed is try to accelerate Microsoft Excel. Basically, in financial world, they have a lot of data. But when they do a lot of data analysis, you cannot use a Microsoft Excel. So you have to accelerate. The way they do that is, the front end use Microsoft Excel, then in back end, you can connect IBM Cell to accelerate. So that's really perfect good case for the acceleration. So they have this case, but we utilize in HPC application. So the IBM software here, I think the good part is they have very nice user interface. So in this particular case, if you have really just two Intel cell blade, we can communicate using IBM DAV to talk to accelerator, and the accelerator talk to DAV. DAV will responsible to make your request and distribute in the accelerator. So it's really nice way to do this under the job distribution. And this really the diagram, you can get the detail, but I want to emphasize here, this right one is the one user code. That's the thing we pay attention. We don't care about how you do this kind of interface or translation. So in this particular case, if you have the, say, C++ code, only thing you want to modify is your .h file. So when you modify the .h file, you can create skeleton of stop code, but that's already the software part. Okay. Another part here really is when you set up this skeleton, you can change this accelerator part to either cell coding or maybe just regular coding without even touch the client side. I think that's very remarkable. So this is real case. We did this. So basically, we have the code as I showed before. We had the code originally run on the Intel. So now we did basically, we first use DAV to farm out to the accelerator. In the case we were not using the SPU, which is really doing additional acceleration. So we got a certain performance, so demonstrate DAV is working. But later on, we simply replace this one with the one with cell implementation, which can get a lot of speed up. We did not touch anything on the client side. I think that's good because think about the client side. If you have, like, say, climate code, which can be maybe 100,000 line of code, you don't want to touch this very often. So here we just use same interface. We change the accelerator, so we can get a performance gain, but without touch the client side. I think that's really a very good feature for this software. And this is the performance we get. So the first one is the DAV built-in the broker. So if you add more accelerator, basically this brokers can distribute to different accelerators. So you really can scale up your performance linearly with number of processors, the accelerator. Okay. The second thing here really is we see the improvement. You know, like you can be like, in this particular case, we can get like 17x improvement. Okay. That's really, really, really good, you know, for whoever people want to spend time doing cell coding. That's very rewarding. But definitely, we see some overhead. But this overhead is now really from software itself. And this is the thing we talk about even in this morning. People talk about data intensive. But people need to remember, when you do the data intensive computing, you have to move your data from your disk to memory to CPU. And even for this computing, for this application, it's already compute intensive, which means I don't need a lot of data come into my accelerator. This already have like up to 50% overhead. So think about people doing so-called petflux data intensive computing. You don't need to buy the accelerator, maybe buy, you know, multi-core processor or whatever. You maybe just need to pay more attention to the communication cost. So for this, we even see this very compute intensive, we already see the 50% overhead. So the thing here really is, in the future, if you want to do any data intensive computing, you have to really make sure the way to transfer data efficiently. Otherwise, that's really your bottleneck. That's really the engineering part. People say is a pin number, but that's really from software. How do you move your data from the hosting processor to accelerate it? You have to really pay attention. But this performance definitely can be improved. Basically, we use IB, infinite band, but if you really use, but the part of infinite band, you only say TCP over infinite band. But if you really real infinite band, probably this overhead can be reduced even more. But that's really not software. It's a data movement that's causing the performance overhead. So just in summary, this really software people try, and it's really nice. But I think the main purpose for this software, if you want to do cell coding, you want to coding a little bit easier inside the cell coding, probably this nice way to help you to connect your x86 to cell processor. But it's really limited. Okay. But MPA is like a programming paradigm. You can use MPA to do a lot of things. So we can see maybe MPA will be widely used, but you know, depending on application. You know, if your application is very hard to break it down, probably this is not a good choice for you. But this, I think, is really between that is really you can do this using this software for the application without in the MPA, which, for example, like Microsoft Excel, you can accelerate with this thing. Another thing is, even for MPA, high-performance computing part, this software is also very useful for this. Thank you.